There's a moment in the history of the universe so profound. It changed everything, but it happened in utter darkness. Picture this: a cosmos so young, so raw, that not a single star had yet ignited. The only light came from the faint afterglow of the Big Bang itself, a ghostly whisper of energy drifting through an endless void. But here's the astonishing part: that light didn't just fade away. It was captured, transformed, and woven into the very bones of the galaxies we see today. This is the story of how the universe, in its infinite creativity, recycled its first light to build the cosmic structures we call home. Think about the last time you turned off a lamp, how the room plunges into darkness, the light seemingly gone forever. But the universe doesn't work like that. That primordial glow, the very first light to ever exist, didn't vanish. Instead, it became something far greater. Over billions of years, it was absorbed by clouds of gas, twisted by gravity, and reborn as the fiery hearts of stars and the swirling arms of galaxies. It's a cosmic recycling program on the grandest scale imaginable, where nothing is wasted, and every photon has a role to play in shaping the cosmos. Why does this matter to us? Because every galaxy, every star, every planet, including our own, carries echoes of that ancient light within it. Understanding how the universe reused its first glow isn't just a tale of astrophysics, it's a clue to our own origins. How did we get here? What forces conspired to turn that early flicker into the dazzling tapestry of the night sky? These questions take us to the edge of human knowledge, where the mysteries of the cosmos meet the ingenuity of those who dare to unravel them. So let's begin this journey together, tracing the path of the universe's first light, from its birth in the fires of creation to its rebirth as the foundation of everything we know. To understand how the universe recycled its first light, we need to travel back to the very beginning, when space and time were so tightly packed together that light couldn't even move freely. Imagine a newborn cosmos just a few 100,000 years old, hotter than the core of any star. Back then, the universe wasn't the vast, transparent expanse we know today. It was more like a thick, glowing soup, a roiling sea of protons, electrons, and light particles, all crashing into each other so violently that photons couldn't travel more than a tiny distance before being absorbed and re-emitted again. But then, something extraordinary happened. As the universe expanded, it cooled slowly at first, then dramatically. The once searing plasma began to calm, and electrons finally had a chance to latch onto protons, forming the very first atoms of neutral hydrogen. This moment, known as recombination, was like a cosmic curtain lifting. Suddenly, light that had been trapped for eons could finally travel unimpeded across space. And that's when the universe lit up for the first time, not with stars, but with a brilliant flash of radiation we now call the cosmic microwave background. This ancient light is still with us today, a faint whisper from the dawn of time. It's everywhere, filling every corner of the cosmos, carrying the secrets of the universe's infancy. When astronomers study this radiation, they're essentially reading a cosmic birth certificate, one that reveals the exact temperature, density, and even the tiny ripples that would one day grow into galaxies. But here's the twist: that light didn't just fade into the background. It became the raw material for everything that followed. Those first photons didn't just escape into nothingness. They collided with matter, transferred energy, and helped shape the early universe. Over time, gravity amplified slight irregularities in the cosmic microwave background, pulling matter together into the first dense clouds. These clouds, enriched by the leftover energy of the primordial light, became the nurseries where stars and galaxies would eventually form. So when you look up at the night sky, you're not just seeing distant suns, you're witnessing the legacy of the universe's first light, reborn in the glow of a trillion stars. The cosmic dark ages were a time of eerie stillness, a universe holding its breath. After that initial burst of light from recombination faded, space became a vast, unlit ocean of hydrogen gas, stretching for billions of light years with no stars to pierce the gloom. Temperatures plunged as the cosmos expanded, and without any new sources of energy, the universe seemed frozen in a state of perfect darkness. But this wasn't the end of the story. It was merely the quiet before a cosmic revolution. Hidden within that sea of neutral hydrogen were tiny seeds, regions where matter had clumped together ever so slightly, thanks to the faint ripples left over from the Big Bang. Gravity, patient and relentless, began pulling these clumps tighter, compressing the gas until it grew denser and hotter. Slowly, imperceptibly, the darkness started to stir. The universe was preparing to reignite itself, not with the afterglow of its birth, but with the fires of its first true stars. What's astonishing is how fragile this transition was. Those first stars, often called population 3 stars, weren't like the ones we see today. They were giants, hundreds of times more massive than our Sun, burning fiercely and dying young in spectacular supernova. Their light didn't just illuminate the cosmos, it ripped apart the surrounding hydrogen gas, blasting it with enough energy to strip electrons from atoms and re-ionize the universe. This marked the end of the Dark Ages and the dawn of a new era where light could travel freely once again. Yet even as these stars blazed to life, they were building something greater. The heavier elements forged in their cores, carbon, oxygen, iron, were scattered across space when they exploded, enriching the gas clouds that would one day form galaxies like our Milky Way. So while the Dark Ages might seem like a void, they were actually a cosmic workshop where the raw materials of everything we know were quietly being assembled. The universe wasn't idle, it was laying the foundation for all that would come. The birth of the first stars wasn't just a flicker in the darkness, it was a cosmic wildfire. Picture these titanic furnaces, hundreds of times more massive than our Sun, blazing to life in the void. Unlike modern stars that contain traces of heavier elements, these primordial giants, population 3 stars, were pure hydrogen and helium, the pristine ingredients left over from the Big Bang. Their nuclear furnaces burned at temperatures we can barely comprehend, fusing atoms with such ferocity that their ultraviolet radiation could rip electrons straight off hydrogen atoms across vast distances. This wasn't merely starlight, it was a demolition crew tearing apart the very fabric of the early universe. What made these stars so revolutionary was their ability to transform space itself. Before their ignition, the universe was filled with neutral hydrogen gas that absorbed light like a cosmic fog. But as these stellar behemoths flooded the cosmos with ultraviolet radiation, they systematically stripped electrons from hydrogen atoms in a process called re-ionization. Imagine sunlight burning off morning mist, except this happened across billions of light years, turning an opaque universe transparent once again. The Dark Ages didn't end with a whimper, but with a cascade of stellar explosions that fundamentally altered how light could travel through space. Yet these stars were paradoxes, brilliant but fleeting. Their enormous mass meant they lived fast and died young, some lasting only a few million years before exploding as supernova. But in their spectacular deaths, they achieved something even more profound. The heavier elements forged in their cores, carbon, oxygen, silicon, were blasted into space, polluting the primordial gas with the building blocks of planets and life. This stellar alchemy transformed the universe from a simple hydrogen soup into a complex chemical laboratory, setting the stage for everything that followed. The echoes of this stellar revolution still shape the cosmos today. When astronomers peer at the most distant quasars, they are seeing light that has traveled through this re-ionized landscape for billions of years. The fingerprints of those first stars are etched into the very transparency of space itself, a testament to how completely they reshaped their universe. And perhaps most astonishingly, without their catastrophic lives and deaths, the raw materials for Earth and for us would never have existed. The universe's first light show didn't just illuminate the darkness, it built the foundation for all future cosmic architecture. These first stars were cosmic alchemists, transforming the simple elements of the early universe into something far more complex. In their cores, where temperatures soared to unimaginable heights, hydrogen and helium fused not just into light and energy, but into entirely new substances. Carbon, oxygen, nitrogen, even iron elements that had never existed before were forged in these stellar furnaces. This wasn't just nuclear fusion, it was the universe learning how to build. When these massive stars reached the end of their short, brilliant lives, they didn't fade quietly. They erupted in cataclysmic supernova, blasting their newly created elements across space like cosmic shrapnel. These explosions were so powerful they could outshine entire galaxies, scattering stardust across thousands of light years. That dust, rich with heavy elements, mixed with the surrounding hydrogen gas, turning what was once a pristine cosmic soup into something far more interesting, a universe filled with potential. Here's where the recycling truly began. That enriched gas didn't just drift aimlessly, gravity pulled it together into new clouds, denser and more chemically diverse than ever before. When these clouds collapsed, they gave birth to a second generation of stars, now containing traces of those heavier elements. Unlike their massive predecessors, these stars could form smaller, cooler, and more stable, some even surrounded by rocky planets made from the very same stardust. But the story doesn't end there. The light from those first stars didn't just vanish either. It was absorbed by gas clouds, heating them, ionizing them, even helping to trigger the birth of new stars. Photons that had traveled across the cosmos were caught and re-emitted, their energy woven into the fabric of growing galaxies. This continuous exchange, matter becoming light, light shaping matter, created a feedback loop of cosmic construction, turning simplicity into complexity over billions of years. We see the legacy of this process everywhere. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged in those early stellar furnaces and scattered by their explosive deaths. Every atom in our solar system, every planet, every living thing carries the fingerprints of that ancient recycling. The universe didn't just make stars, it used them as factories, turning raw hydrogen into the ingredients for everything we know. And it all started with those first fleeting giants, whose brief lives set the stage for the rich, diverse cosmos we see today. While the first stars were lighting up the cosmos, something far more mysterious was at work behind the scenes, an invisible force shaping everything from the shadows. Dark matter, which neither emits nor absorbs light, was the universe's silent architect. Think of it like this. If ordinary matter were the bricks and mortar of galaxies, dark matter was the blueprint, the unseen framework determining where those structures would rise. Without its gravitational pull, the gas clouds enriched by those early stars might have drifted forever, never collapsing into the galaxies we recognize today. Here's what's fascinating: dark matter didn't just nudge things along. It created the cosmic infrastructure. Tiny fluctuations in the early universe, imprinted during the Big Bang, were amplified by dark matter's gravity, forming vast webs of matter known as the cosmic web. Along these filaments, gas pooled into dense knots, and it was in these knots that the first galaxies took shape. Ordinary matter, the stuff we can see, simply followed the trails dark matter had already laid out, like water flowing into valleys carved by an unseen hand. But dark matter's role wasn't just about brute force. Its distribution determined the destiny of galaxies. In regions where dark matter clustered tightly, galaxies grew massive and dense like modern-day ellipticals. Where it was more diffuse, spirals like our Milky Way took shape, their delicate arms tracing the gentler pull of their invisible halos. Even today, dark matter continues to steer the evolution of galaxies, holding them together against the centrifugal forces that might otherwise tear them apart. The irony is profound. The very substance that makes up most of the universe's mass remains invisible to us, detectable only through its gravitational fingerprints. Yet without it, the night sky would be empty, no glittering spirals, no glowing nebulae, no planets orbiting distant stars. Dark matter didn't just guide the recycling of light, it made sure there were structures for that light to illuminate. So when we gaze at the stars, we're not just seeing the aftermath of cosmic recycling, we're witnessing the legacy of an invisible hand that shaped everything. Galaxies didn't just appear fully formed, they grew like cosmic snowballs, gathering mass and structure over billions of years. Picture those first proto-galaxies, tiny sparks in the void, each one a messy knot of gas and stars swirling within its dark matter cocoon. They were nothing like the majestic spirals or glowing ellipticals we see today, more like rough sketches of what galaxies could become. But within their chaos lay the seeds of everything familiar. As these infant galaxies drifted through the early universe, they didn't stay isolated for long. Gravity, the great architect of the cosmos, pulled them together in slow-motion collisions. When two proto-galaxies merged, their gas clouds crashed like tidal waves, triggering bursts of new star formation. With each merger, they grew larger and more complex, accumulating not just stars but also the recycled stardust from earlier generations. This wasn't destruction, it was cosmic reinvention, where every collision added another layer to the story. But here's the twist. The stars forming inside these galaxies didn't just passively watch the show. Their intense radiation acted like cosmic blowtorches, reheating the surrounding gas and pushing it outward in powerful winds. This created a feedback loop, stars ionizing gas, which then resisted further collapse, regulating how quickly new stars could form. Without this balancing act, galaxies might have burned through their fuel too quickly, leaving the universe dark and empty. Instead, they grew in a controlled simmer, conserving their resources over billions of years. The recycled light from those early stars played a surprising role too. As it streamed outward, it illuminated nearby gas clouds, subtly influencing where and when new proto-galaxies could take shape. Imagine a chain reaction where each generation of stars altered the environment for the next, carving out bubbles of ionized gas that either encouraged or stifled future galaxy growth. This delicate interplay of light and matter turned the universe into a dynamic workshop, where every action rippled across cosmic time. Today, we see the results of this grand experiment everywhere, from the dwarf galaxies clinging to the edges of our Milky Way to the colossal ellipticals at the hearts of galaxy clusters. Each one tells a different chapter of the same story, how gravity, dark matter, and recycled starlight conspired to turn simplicity into staggering diversity. And the process isn't over. Even now, galaxies continue to collide, merge, and evolve, carrying forward the legacy of those first chaotic fragments. When we look deep into space, we're not just seeing static snapshots, we're watching a universe still learning how to build itself. The universe has a remarkable way of balancing its own chaos. like a master chef constantly adjusting the heat to prevent a cosmic stew from boiling over. Take star formation, for example. It's not some runaway explosion of activity. Instead, it's a finely tuned dance where stars themselves control the tempo. When a new generation of stars ignites, their intense radiation acts like a cosmic stop sign, blasting nearby gas clouds with so much energy that they heat up and disperse. This temporarily puts the brakes on creating more stars, giving galaxies a chance to catch their breath. But the story doesn't end there. Those same massive stars, after burning bright and fast, eventually explode as supernova. And here's the twist: their violent deaths don't just scatter heavy elements into space. They also send shockwaves rippling through surrounding gas, compressing it like an invisible hand squeezing a sponge. These shockwaves create dense pockets where gravity takes over, collapsing the gas into new stellar nurseries. It's a cycle of destruction and rebirth, where the end of one star's life becomes the spark for another's beginning. This feedback loop is why galaxies don't just burn out after a single burst of star formation. Without it, galaxies would exhaust their gas reserves in a fiery frenzy, leaving the universe dark and lifeless far too soon. Instead, the process stretches across billions of years, allowing galaxies to grow gradually, layer by layer. Think of it like a forest regenerating after a wildfire. The flames clear the way for new growth, ensuring the ecosystem thrives over time rather than collapsing. The most fascinating part: this cycle isn't just random chaos. It's a delicate equilibrium where the energy output of stars fine-tunes the rate at which new ones can form. Too much radiation and star formation stalls, too many supernova, and gas gets compressed too quickly, leading to bursts of frantic stellar birth. But when balanced just right, galaxies evolve steadily, building up their structure while conserving fuel for the long haul. We see evidence of this self-regulation everywhere in the way spiral galaxies like our Milky Way maintain their graceful arms, or how dwarf galaxies flicker with sporadic bursts of star formation. Even today, supernova remnants and stellar winds continue shaping the interstellar medium, ensuring the cosmic recycling program never grinds to a halt. It's a reminder that the universe isn't just expanding, it's constantly refining itself, turning destruction into creation, and ensuring the story of starlight never truly ends. Quasars are like the universe's ultimate recycling plants, cosmic engines of unimaginable power that reshape everything around them. At their cores lurk supermassive black holes, billions of times heavier than our sun, devouring gas and dust at a staggering rate. But here's the paradox: as matter spirals toward oblivion, it doesn't just vanish. Friction heats it to millions of degrees, creating blazing disks of plasma so bright they outshine entire galaxies. This isn't just light. It's a torrent of energy that floods the cosmos, pushing gas outward at nearly the speed of light in colossal jets that stretch for thousands of light years. What makes quasars so fascinating isn't just their raw power, but how they repurpose it. Those searing jets and radiation winds act like cosmic bulldozers, sweeping through their host galaxies and blasting gas far into intergalactic space. At first glance, this seems catastrophic, like a wildfire clearing a forest. But just as fires replenish soil, quasars enrich the universe. The gas they expel carries heavy elements forged in earlier generations of stars, scattering them across vast distances where they'll eventually cool and form new stars, planets, and even the raw materials for life. Quasars also play the role of cosmic regulators. By heating surrounding gas, they prevent it from collapsing too quickly into new stars. It's a delicate balance: too much quenching, and star formation halts entirely; too little, and galaxies burn through their fuel too fast. But when tuned just right, this feedback ensures galaxies grow steadily over billions of years rather than flaming out in a brief, brilliant burst. We see echoes of this process in modern galaxies like our own, where supermassive black holes, though now quiet, once shaped their evolution through similar outbursts. The reach of quasars extends far beyond their immediate surroundings. Their light travels unimpeded for billions of years, illuminating gas clouds along the way like a cosmic flashlight. Astronomers use this backlighting to map the universe's hidden structure, revealing the vast filaments of the cosmic web where matter congregates. Even more remarkably, some of that ancient quasar light gets absorbed and re-emitted by distant gas clouds, effectively recycling photons that began their journey when the universe was young. So while quasars might seem like agents of destruction, they're actually master recyclers sculpting galaxies, seeding future star formation, and even helping to weave the universe's large-scale structure. Their brilliance isn't just a spectacle, it's a fundamental force in the story of how the universe builds itself. Every time we detect the glow of a distant quasar, we're witnessing a chapter in that grand narrative, one where even the most violent processes contribute to the delicate balance of cosmic creation. There's a hidden architecture to the cosmos, an intricate tapestry woven from threads of dark matter and glowing gas, stretching across billions of light years. This is the cosmic web, the universe's grand design. Picture it like a colossal spider's silk, but instead of sticky threads, these filaments are highways of matter, funneling gas and galaxies toward dense intersections where clusters blaze like cities in the night. The voids between them, not empty at all, but vast deserts where matter is so sparse, a single atom might drift for millions of years without meeting another. This web didn't form by accident. Its blueprint was drawn in the first moments after the Big Bang, when quantum ripples, tiny fluctuations in density, were frozen into the fabric of space. Over billions of years, gravity amplified those faint wrinkles, pulling matter into dense knots along the filaments while leaving the voids behind. It's a slow-motion artwork painted by the relentless tug of dark matter, with ordinary matter simply following its lead like iron filings drawn to a magnet. The cosmic web isn't just a static sculpture, it's alive with motion. Gas streams along these filaments, flowing toward galaxies like rivers feeding a sea. When those rivers collide, they trigger fireworks of star formation, igniting galaxies with new light. Some of that light escapes into the voids, where it illuminates the web's faintest threads like a flashlight beam cutting through fog. Astronomers call this the Lyman alpha forest, a telltale pattern of absorption lines in quasar light that reveals the web's hidden structure. But the web's true brilliance lies in its scale. The largest filaments stretch so far that light takes hundreds of millions of years to travel their length. They curve and twist, connecting galaxy clusters in a network so vast it defies imagination. Even more astonishing, we're part of it. The Milky Way sits on a filament's edge, a single thread in this cosmic tapestry, with the Virgo cluster glowing at one end and the vast emptiness of the local void stretching beyond. Mapping this web isn't just about understanding where things are. It's about decoding how the universe grows. By tracing its structure, we can see how galaxies evolve in dense knots versus sparse filaments, how gas cycles in and out of voids, even how dark matter's gravity sculpts the paths of light itself. The cosmic web is more than a map, it's a chronicle of the universe's past and a forecast of its future, written in the language of gravity and light. And every time we peer deeper, we uncover another piece of its story. Galaxies might seem like solitary islands in the void, but they're more like cosmic nomads, forever drifting toward one another in a slow-motion dance orchestrated by gravity. When two galaxies meet, it's not a gentle handshake, it's a spectacular merger, a celestial tangle where their stars, gas, and dark matter halos intertwine over hundreds of millions of years. Picture the Milky Way and Andromeda, our nearest galactic neighbor, currently hurtling toward each other at 200,000 miles per hour. In about 4 billion years, they'll collide, their spiral arms twisting into chaos before settling into a single, colossal elliptical galaxy. This isn't science fiction, it's the inevitable fate of most galaxies, a process so common it's shaped the universe we see today. What happens during these mergers is nothing short of cosmic alchemy. As galaxies spiral inward, their gas clouds slam together like tidal waves, compressing under unimaginable pressure. These collisions trigger fireworks of star formation, turning dormant hydrogen into blazing stellar nurseries. Some of the most luminous galaxies we observe, starburst galaxies, are products of this violent creativity, shining hundreds of times brighter than normal as they churn out new stars at a frenetic pace. The light from these newborn stars isn't just spectacle, it's recycled energy, photons carrying the legacy of ancient supernova and quasar winds, now reignited in fresh stellar furnaces. But mergers don't just create, they also transform. Smaller galaxies, like cosmic snacks, are devoured by larger ones. Their stars are scattered into halos, their gas funneled toward the center to feed supermassive black holes or fuel future star birth. This galactic cannibalism isn't random destruction, it's a precise rebuilding process. Take the giant elliptical galaxies at the hearts of clusters. These smooth, featureless behemoths didn't form quietly. They're the survivors of countless mergers, their chaotic pasts erased by relentless collisions that erased their spiral arms and left behind a uniform glow. Even our Milky Way bears the scars of this carnivorous history. Wrapped around its disk are streams of stars, the mangled remains of dwarf galaxies it absorbed over billions of years. The Sagittarius dwarf, for example, is currently being torn apart by our galaxy's gravity, its stars smeared into a shimmering arc across the sky. These mergers aren't just ancient history, they're ongoing, a reminder that galaxies are never finished evolving. The irony is profound. The same mergers that tear galaxies apart also give them new life. Without these collisions, the universe would be filled with tiny, unevolved galaxies, never growing large enough to host complex stellar populations or habitable planets. Galactic cannibalism isn't just a side effect of cosmic evolution, it's the engine that built the vibrant, diverse universe we call home. Every time we look up at the night sky, we're seeing the aftermath of these epic collisions, a testament to the universe's relentless creativity. At the center of nearly every galaxy, including our own Milky Way, lurks a gravitational monster, a supermassive black hole with the mass of millions or even billions of suns crushed into a single point. But these aren't just cosmic vacuums silently devouring everything around them. They're dynamic engines capable of shaping their entire galaxies in ways we're only beginning to understand. Take Sagittarius, a star, the black hole at our galaxy's core. Though quiet now, its occasional flares reveal an astonishing truth: even dormant black holes can wake up and dramatically alter their surroundings. When supermassive black holes feed, they don't just swallow matter quietly. Gas spiraling toward the event horizon forms a searing accretion disk, heated to millions of degrees by friction and magnetic fields. This process converts matter into energy with terrifying efficiency. Up to 40% of the mass gets transformed into radiation, compared to just 0.7% for nuclear fusion in stars. The result: quasars and active galactic nuclei that can outshine every star in their galaxy combined, visible across billions of light years. But their true impact lies not in their brightness, but in how they channel that energy back into their cosmic neighborhoods. Some black holes act like cosmic blowtorches, shooting jets of plasma at nearly light speed from their poles. These jets can span millions of light years, plowing through interstellar gas like a tsunami. Where they strike, they compress gas clouds, triggering bursts of star formation in their wake. Yet in other regions, the same black hole's heat surrounding gas so intensely it can't cool and collapse into stars at all. This creates a feedback loop where the black hole's own appetite regulates star formation across the entire galaxy. Too much activity and star birth shuts down. Too little and stars form unchecked. The delicate balance between these extremes determines whether a galaxy remains a vibrant star factory or becomes a quiet, aging relic. We see this cosmic balancing act playing out in galaxy clusters, where the central black hole's outbursts prevent gas from cooling too quickly and forming stars all at once. These periodic eruptions lasting millions of years create vast bubbles in the cluster's gas, visible in X-ray observations. Like a cosmic thermostat, they maintain the perfect conditions for gradual galaxy evolution rather than sudden, unsustainable bursts. Without this regulation, galaxies might exhaust their gas reserves in a single frenzied epoch of star formation, leaving the universe dark and lifeless far too soon. Perhaps most remarkably, black holes may have helped build the very galaxies they inhabit. In the early universe, their intense radiation and powerful winds could have provided the push needed to gather gas into dense clouds where the first stars and proto-galaxies formed. Their gravity might have served as anchor points around which galaxies assembled. Even today, the mergers of supermassive black holes detectable through gravitational waves may redistribute angular momentum in ways that shape galactic structure. Far from being mere destroyers, these gravitational giants could be the unseen architects of cosmic order, their invisible hands guiding the growth of everything around them. The relationship between black holes and galaxies is one of mutual creation and control, a dance where each partner shapes the other over billions of years. When we observe distant quasars blazing across the cosmos, we're not just seeing voracious monsters, we're witnessing the heartbeat of galaxy evolution itself, a pulse of energy that has shaped every shining city of stars we see today, including our own place in the Milky Way. Dark energy is the universe's silent game changer, an invisible force pushing galaxies apart at an ever-increasing pace. Right now, we can still see the light from distant galaxies, photons that have traveled billions of years to reach us. But as dark energy accelerates the expansion of space, those photons will face a cosmic hurdle they can't overcome. The space between us and those galaxies isn't just growing, it's stretching the very fabric of reality, shifting their light to longer, redder wavelengths. Over time, that redshift will stretch their glow beyond detection, turning today's vibrant cosmic web into a fading memory. This isn't just about distant galaxies disappearing from view. It's about the loss of cosmic history, the recycled light from the first stars and quasars photons that have bounced between gas clouds and galaxies for eons will gradually become too faint to observe. Future astronomers might peer into the sky and see only darkness beyond our local galactic neighborhood, with no trace of the universe's fiery beginnings. The cosmic microwave background, that faint echo of the Big Bang, will redshift into oblivion, erasing the universe's birth certificate. But here's the paradox: even as light fades, the universe's expansion ensures that matter, once bound by gravity, will be torn apart. Galaxy clusters held together by their mutual pull will eventually drift beyond each other's reach. Stars within galaxies will grow isolated as the space between them stretches. Over trillions of years, the night sky will empty, leaving civilizations like ours, if any, still exist, with no evidence that other galaxies ever existed. The universe won't just grow dark, it will become unknowable. Yet this grim fate isn't entirely absolute. While distant light may vanish, the legacy of recycled photons isn't lost. The elements forged in stars and scattered by supernova carbon, oxygen, iron will endure, woven into new generations of stars and planets. The universe's first light may fade, but its fingerprints remain in the chemistry of everything around us. Future civilizations might not see the glow of distant galaxies, but they could still uncover the universe's history by studying the atoms in their own cosmic backyard. The accelerating expansion raises deeper questions about how we understand the cosmos. Right now, we live in a privileged era, one where we can still observe the universe's infancy and trace its evolution. But in 1 trillion years, that window will close. The evidence we take for granted, the redshift of galaxies, the cosmic microwave background, will be gone. It's a humbling thought. We exist in a brief sliver of cosmic time when the universe's story is still legible. That realization doesn't just change how we see the cosmos, it underscores the urgency of studying it now before the lights go out for good. The James Webb Space Telescope isn't just another observatory, it's a time machine designed to capture light that's been traveling for over 13 billion years. When it peers into the deepest corners of the cosmos, it's not just seeing distant galaxies, it's witnessing their infancy, a snapshot of the universe when it was barely a toddler. These ancient photons, stretched and dimmed by their epic journey across expanding space, carry secrets about how the first starlight was absorbed, scattered, and reborn into new celestial structures. Every faint glow Webb detects is a puzzle piece, revealing how the universe learned to build galaxies from the ashes of its own primordial fire. What makes these observations so revolutionary is their precision. Earlier telescopes like Hubble gave us glimpses of early galaxies, but they were like trying to read a book through fog. The details were blurred, the context unclear. Webb cuts through that haze with its infrared eyes, sensitive enough to detect the heat signatures of stars that died before Earth even formed. By analyzing the chemical fingerprints in their light, astronomers can trace how these early galaxies processed the universe's first heavy elements. Did they spew them out in supernova winds? Did they trap them in swirling disks where new stars could form? The answers are written in the wavelengths of light we're only now beginning to decode. One of Webb's most startling discoveries is just how bright some of these early galaxies were, brighter than our models predicted. This suggests that star formation in the infant universe wasn't a slow simmer but a roaring blaze, with galaxies recycling their gas into stars at breakneck speeds. Some even show evidence of massive black holes at their cores, far earlier than expected. These findings are forcing scientists to rethink how quickly cosmic structures could assemble, and whether dark matter played a more dynamic role in clustering matter than we'd assumed. But Webb isn't working alone. Ground-based telescopes like the ALMA array in Chile are complementing its vision, studying the cold dust and gas between stars, the raw material for future galactic recycling. Together, they're painting a multidimensional picture, not just where the first light came from, but how it interacted with its surroundings. For example, when Webb spots a distant galaxy, ALMA can examine the carbon monoxide molecules in its gas clouds, revealing how efficiently that galaxy was converting primordial hydrogen into the building blocks of planets and life. Every new observation is a humbling reminder of how much we don't know. Some galaxies from this era appear shockingly mature, as if they'd aged billions of years in a cosmic blink. Others seem to be missing key heavy elements, suggesting their light never fully mixed with the surrounding universe. These outliers aren't just curiosities, they're clues that the early cosmos might have had multiple pathways for recycling light, each leaving a distinct imprint on the galaxies we see today. The ultimate goal isn't just to catalog these ancient objects, but to understand the feedback loops that shaped them. How did the radiation from the first stars clear the cosmic fog? How did black holes regulate star formation in their host galaxies? Each answer Webb provides is like turning a page in a cosmic instruction manual, showing us not just how the universe built its first structures, but how those structures eventually led to us. And with every new discovery, we're not just observing history, we're rewriting it. There's a cosmic detective story unfolding in the deepest reaches of space, one where the evidence isn't just hard to find, it's vanishing before our eyes. Astronomers call it the missing satellites problem, and it's one of the most puzzling gaps in our understanding of galaxy formation. Here's the mystery. Supercomputer simulations of the early universe predict that hundreds of small, dwarf galaxies should orbit larger ones like the Milky Way. But when we look, we only spot a handful. It's as if the universe left behind a trail of breadcrumbs, only for most of them to disappear. So where did these galaxies go? The answer might rewrite what we know about the cosmic dark ages and how light shaped the universe's first structures. One possibility is that these galaxies aren't truly missing, they're just hiding. The smallest, faintest dwarfs could be cloaked in clouds of neutral hydrogen gas, the same material that once filled the universe before stars ignited. Like fog obscuring a street lamp, this gas might absorb their starlight before it reaches our telescopes. But there's a twist. If that's true, it means these galaxies are cosmic time capsules, preserving conditions from an era when the universe was still learning how to build. Their dim glow could hold clues about how the first photons interacted with matter, sculpting the cosmic web we see today. Another theory takes us back to the violence of the early universe. Perhaps many of these dwarfs were torn apart by tidal forces or blasted apart by supernova before they could grow. Imagine a fledgling galaxy, barely holding itself together, when a nearby supernova's shockwave rips through its gas clouds, scattering them into the void. Without enough mass to cling to, these fragments might never coalesce into something detectable. If so, the missing satellites aren't lost, they're ghosts, their material absorbed by larger galaxies or dissolved into the intergalactic medium. Yet the most intriguing explanation involves dark matter. Simulations suggest these dwarfs should be nestled inside dense halos of invisible matter. But what if dark matter behaves differently on small scales? Some models propose that dark matter particles interact weakly with each other, smoothing out the clumps that would normally anchor dwarf galaxies. Without these gravitational anchors, the gas that might have formed stars simply drifted away, leaving behind dark, starless husks too faint to see. If confirmed, this would mean the missing galaxies aren't just a puzzle, they're a fingerprint, revealing the hidden rules governing dark matter itself. The hunt for these elusive dwarfs is pushing telescopes to their limits. Projects like the Vera C. Rubin Observatory are scanning the sky for ultra-faint galaxies, some containing just a few hundred stars. Others are searching for indirect traces, like ripples in the Milky Way's outer halo, gravitational echoes of long-absorbed satellites. Every discovery, or even every non-discovery, tightens the constraints on our models of cosmic evolution. What's at stake isn't just a census of dwarf galaxies. Solving this mystery could unravel how light escaped the early universe's fog, how dark matter shaped cosmic structures, and even why galaxies like ours exist at all. The missing satellites aren't just gaps in our maps, they're missing chapters in the story of how the universe recycled its first light into the galaxies we know today. And like any good mystery, the answer might be hiding in plain sight, waiting for the right tool, the right observation to bring it into focus. Magnetic fields are the invisible sculptors of the cosmos, threads of force weaving through galaxies, quietly shaping their destiny. While gravity and dark matter dominate the conversation about cosmic structure, Magnetism works behind the scenes, guiding the flow of gas like an unseen hand. Picture a vast interstellar cloud poised to collapse into stars. Without magnetic fields, it would crumple chaotically. But these fields act like cosmic scaffolding, channeling the gas into orderly filaments and slowing its collapse just enough to regulate star formation. The result, a galaxy that doesn't burn out too quickly, but instead matures steadily, its stellar birth spaced across billions of years. The origins of galactic magnetic fields are one of astronomy's great unsolved puzzles. Some theories suggest they began as faint ripples in the primordial plasma. Quantum fluctuations stretched to cosmic scales during the universe's rapid expansion. Others propose they were jumps started by the first generation of stars, whose violent death seeded space with ionized gas and turbulent currents. As these charged particles moved, they created electric currents, which in turn generated magnetic fields, a self-reinforcing cycle that amplified weak fields into the powerful forces we observe today. Imagine a dynamo the size of a galaxy, spinning for eons, quietly building strength until its influence became undeniable. These fields don't just linger passively, they actively shape their surroundings. In spiral galaxies like the Milky Way, magnetic fields align with the arms, reinforcing their structure and helping channel gas towards star-forming regions. They also influence cosmic rays, those high-energy particles racing through space. Without magnetic fields, these rays would zip straight out of galaxies, but instead, the fields bend their paths, trapping them in a turbulent dance that spreads energy across vast distances. This process isn't just about containment, it's about redistribution. Cosmic rays heated by magnetic fields can prevent gas clouds from cooling too quickly, subtly regulating where and when new stars ignite. The evidence for these invisible forces is etched into the sky. Polarization measurements reveal how dust grains align with magnetic fields, while radio telescopes trace the synchrotron radiation emitted by electrons spiraling along magnetic lines. Even the delicate filaments of gas in galaxy clusters bear the imprint of magnetism, their structures more ordered than gravity alone could explain. The Atacama Large Millimeter Array has captured stunning images of magnetic fields threading through star-forming clouds, their patterns resembling intricate fingerprints, each one unique, each one telling a story of how chaos becomes cosmos. Yet mysteries remain. Why do some galaxies host magnetic fields thousands of times stronger than others? How did fields grow so quickly in the early universe, appearing fully formed even in galaxies just 1 billion years old? The answers might lie in the interplay between supermassive black holes and their surroundings, or in the turbulent wakes of galaxy collisions. What's clear is that magnetic fields aren't just a footnote in the story of cosmic recycling, they're a dynamic character, shaping the flow of matter and energy from the smallest clouds to the largest galactic superstructures. The next time you gaze at the Milky Way's shimmering band, remember, you're not just seeing stars, you're witnessing the aftermath of an ancient magnetic symphony, one that continues to play unseen beneath the surface of the night. The universe didn't wake up gently, it burst into existence with a cosmic fireworks show. The Epoch of Re-ionization was that pivotal moment when the first stars and galaxies tore apart the veil of neutral hydrogen that had shrouded the cosmos since its infancy. Imagine a fog so thick it absorbed every photon, trapping light in a perpetual twilight. Then, suddenly, brilliant beacons pierced through, their ultraviolet radiation blasting electrons off hydrogen atoms like a stellar hurricane clearing mist from a mountaintop. This wasn't just a change in lighting, it was a fundamental rewrite of the universe's rules, transforming it from an opaque void into the transparent expanse we know today. What's astonishing is how quickly this happened, cosmically speaking. After nearly 400 million years of darkness, the first stars flickered to life, but within just a few 100 million more, their collective glow had ionized almost every hydrogen atom in existence. Think of it like dominoes falling. Once a few massive stars ignited, their radiation created bubbles of ionized gas that expanded outward, overlapping and merging until the entire cosmos was alight. These bubbles weren't uniform, though. Some regions reionized early, others late, leaving a patchwork quilt of transparency that astronomers are still mapping today through the faint whispers of ancient quasar light. The heroes of this story population, 3 stars, were unlike anything in the modern universe. Born from pristine hydrogen and helium, they burned at temperatures so extreme their ultraviolet radiation could strip electrons from atoms across thousands of light years. But their brilliance came at a cost. These stars lived fast and died young, exploding as supernova that seeded space with heavier elements. Their deaths weren't just an end, they were a catalyst, shock waves from their explosions compressing nearby gas clouds and triggering new rounds of star formation. It's a feedback loop written in light and plasma, stars ionizing gas, gas collapsing into new stars, and each generation altering the cosmic landscape for the next. Studying this epoch isn't just academic curiosity, it's forensic science on a galactic scale. When astronomers train telescopes like Webb on the most distant quasars, they're looking for shadows. As that quasar light passes through the last remnants of neutral hydrogen, it leaves absorption lines in its spectrum, dark bands that reveal where and when the fog lifted. Each line is a timestamp telling us which regions ionized first and how the process spread. Some quasars show clear lines, meaning their light traveled through patches of lingering neutral gas. Others shine unobstructed, their path cleared by the relentless radiation of early galaxies. But the Epoch of Re-ionization wasn't just about stars. Supermassive black holes growing in the hearts of those first galaxies likely played a role too. Their quasars pumped out X-rays that could penetrate deep into neutral gas, pre-ionizing regions that starlight alone couldn't reach. This might explain why reionization happened faster in some areas, black holes and stars working in tandem, their combined radiation dismantling the cosmic fog from multiple angles. The echoes of this upheaval are everywhere. The cosmic microwave background carries faint polarization patterns, imprints of how those first photons scattered off free electrons during reionization. Even the distribution of galaxies today reflects this ancient transition, with voids and clusters tracing the outlines of those long-vanished ionized bubbles. It's as if the universe left us a diary written in the language of light and shadow, waiting for us to decode its secrets. Understanding this epoch isn't just about looking back, it's about seeing our own origins in context. The same processes that cleared the cosmic fog also set the stage for galaxies like ours to form. Without reionization, gas would have remained too diffused to collapse efficiently, leaving the universe forever dark and sterile. But thanks to those first stars and their explosive legacy, light won its freedom and, in doing so, laid the foundation for everything that followed, from spiral galaxies to planets to life itself. The Epoch of Re-ionization wasn't just the universe waking up, it was the moment it learned how to shine. The first stars were cosmic alchemists of the purest kind, massive furnaces fusing hydrogen and helium into something entirely new. But when these titans reached the end of their short, brilliant lives, they didn't just fade away. They exploded with such violence that their cores became crucibles, forging elements heavier than anything the universe had ever seen. Carbon, oxygen, neon, even gold and uranium, all were born in the heart of supernova, scattered across space like seeds in a cosmic wind. This wasn't just destruction, it was the universe learning how to build complexity from simplicity. Think about the iron in your blood or the calcium in your bones. Every atom of these elements was once part of a star that died billions of years ago. When those first supernovae erupted, they didn't just spew debris, they launched a recycling program of staggering scale. Their shockwaves plowed through surrounding gas clouds, compressing them and enriching them with these newly minted heavy elements. Over time, that enriched gas collapsed into new generations of stars, each one carrying traces of its ancestors' ashes. And with each cycle, the universe grew more chemically diverse, eventually creating the raw materials for rocky planets and life itself. Astronomers can actually trace this lineage through light. When a star dies, it imprints its chemical fingerprint onto the light it emits. By analyzing the spectra of distant supernova, we see absorption lines, dark bands that reveal exactly which elements were present in the explosion. It's like reading a cosmic barcode, one that tells us not just what the star was made of, but how it lived and died. Some of these spectral lines correspond to elements like silicon or sulfur, forged in the star's final moments. Others, like oxygen or carbon, were crafted earlier in its life and flung outward during the explosion. Together, they form a story written in light, one that's traveled across billions of years to reach us. The most astonishing part, this process is still happening today. When we look at the Crab Nebula, the remnant of a supernova observed in 1054, we're seeing freshly minted heavy elements mixing with interstellar gas. In a few million years, that material will become part of new stars and planets, continuing the cycle. Even our own solar system bears the marks of this recycling. Meteorites contain isotopes like aluminum-26, which could only have formed in the heart of a dying star just before our sun ignited. This connection between stars and life isn't just poetic, it's foundational. Without those first supernova, Earth would be a very different place. No carbon for organic molecules, no oxygen for water, no iron for a molten core to generate a protective magnetic field. The universe would still be a sea of hydrogen and helium, devoid of planets, let alone life. Every time you take a breath or feel your heartbeat, you're interacting with atoms that were once part of a star's final, cataclysmic moments. And the light from those ancient explosions, it's still traveling, carrying the signatures of those first heavy elements across the cosmos. When astronomers detect that light, they're not just observing history, they're piecing together the recipe that made our existence possible. The iron in our blood, the silicon in our rocks, even the gold in our jewelry, all were forged in stellar deaths that lit up the early universe. In the grand story of cosmic recycling, we're not just observers. We're the products of stars that died so we could live. Galactic winds are nature's way of hitting the reset button, violent gusts of gas and radiation that blast out from galaxies at millions of miles per hour, carrying the raw ingredients of star formation into the void. Picture a supernova exploding with such force that it doesn't just light up its host galaxy, it propels entire clouds of gas beyond the galaxy's gravitational grip. Or imagine a supermassive black hole devouring matter so furiously that it belches out jets of plasma, carving through interstellar space like a cosmic sandblaster. These outflows aren't just dramatic spectacles, they're essential regulators preventing galaxies from burning through their fuel reserves too quickly and collapsing under their own weight. What makes these winds so fascinating is their dual-natured, destructive yet creative. On one hand, they strip galaxies of the very gas needed to form new stars. The starburst galaxy Messier 82, for example, is losing gas 10 times faster than it's converting it into stars, with winds so powerful they've been detected over 30,000 light-years from its core. Yet this same expulsion enriches intergalactic space with heavy elements, scattering carbon, oxygen, and iron far beyond their birthplace. Over time, this recycled material cools and falls back into galactic halos or neighboring galaxies, fueling future generations of stars. It's a galactic-scale version of composting, waste from one region becoming nourishment for another. The light from these outflows tells a hidden story. When astronomers analyze the spectra of galactic winds, they don't just see random noise, they find distinct absorption lines revealing the composition, speed, and even temperature of the ejected gas. In some cases, like the nearby Pinwheel galaxy, these winds glow in X-rays, betraying the presence of gas heated to millions of degrees by shock waves. Other outflows, like those from quasar host galaxies, emit polarized light, hinting at the tangled magnetic fields guiding their expansion. Each wavelength unveils a new layer of the wind's structure, from the cold molecular clouds riding the outflow to the scorching plasma trailing behind. Without these outflows, galaxies would face a cosmic dead end. Simulations show that without winds to vent excess energy, gas would collapse directly into a galaxy's center, forming stars in an unsustainable frenzy before exhausting all available fuel. The result, a universe filled with red and dead galaxies, aging stellar populations with no fresh gas to birth new stars. Instead, outflows create balance. By ejecting some material, they slow star formation to a sustainable trickle, allowing galaxies to evolve gradually over billions of years. The Milky Way itself may owe its spiral structure to past outflows that prevented its gas from clumping too densely. Perhaps most remarkably, these winds don't just shape individual galaxies, they connect them. The COS Halos survey revealed that the space around galaxies is crisscrossed with filaments of gas, much of it enriched by ancient outflows. This intergalactic medium isn't just a passive backdrop. It's a dynamic reservoir storing recycled material until gravity pulls it back into the cosmic web. Some astronomers even speculate that the gas fueling today's star formation might have been expelled by a distant galaxy over 10 billion years ago, completing a journey across unimaginable distances. The next time you gaze at the delicate arms of a spiral galaxy, remember, its beauty isn't just the work of gravity. It's the product of countless tempest stellar explosions and black hole gales that sculpted its growth, leaving behind not just light, but the very elements that make our existence possible. Galactic winds aren't just cosmic weather, they're the breath of the universe itself, exhaling the past to inhale the future. Dwarf galaxies might be small, but they punch far above their weight in the cosmic story. These faint, unassuming collections of stars and gas are the universe's original building blocks, the leftover scraps from an era when galaxies were just beginning to take shape. Think of them as cosmic fossils, preserving clues about how the largest structures in the universe were assembled piece by piece. While massive spirals like the Milky Way steal the spotlight, it's often these diminutive dwarfs that hold the keys to understanding galactic evolution. Their unassuming glow carries echoes of the past, revealing how light and matter were recycled over billions of years. Many of these dwarfs met dramatic fates, swallowed whole by larger galaxies in slow-motion collisions that played out over eons. When a dwarf galaxy merges with a giant like the Milky Way, it doesn't just vanish. Its stars are strewn across the galactic halo, forming shimmering streams that trace the orbits of their long-lost homes. The Sagittarius dwarf spheroidal, for example, is currently being torn apart by our galaxy's gravity, its stars smeared into a delicate arc across the southern sky. These stellar graveyards aren't just hauntingly beautiful, they're history books written in starlight, chronicling the Milky Way's growth through countless mergers. Yet some dwarfs avoided assimilation, surviving as faint satellites orbiting their larger cousins. The Large and Small Magellanic Clouds, visible from Earth's southern hemisphere, are prime examples, irregular dwarfs still brimming with gas and young stars. Unlike their dissolved siblings, these galaxies remain active, their star-forming regions glowing brightly enough to be seen with the naked eye, but even they aren't untouched by their giant neighbors. Tidal forces from the Milky Way warp their shapes, stripping away gas that forms a shimmering bridge between them, a celestial umbilical cord feeding material into our galaxy's future stars. What makes these dwarfs so valuable to astronomers isn't just their role as galactic snacks. Their chemical compositions are time capsules from the early universe. Many lack heavy elements, suggesting they formed before supernova had thoroughly enriched cosmic gas. Others, like the ultra-faint dwarfs orbiting the Milky Way, are so pristine they're essentially living relics of the universe's first star-forming environment. When we study their spectra, we're glimpsing the raw ingredients of galaxy formation, hydrogen and helium nearly untouched by stellar alchemy. The light from these dwarfs tells another story too, one of resilience and adaptation. Despite their small size, many have managed to cling to reservoirs of gas, defying the gravitational tides and ultraviolet radiation that should have stripped them bare. Some, like the dwarf galaxy Leo T, even host pockets of star formation despite containing just a few million stars total. Their ability to recycle their own light and material, generating new stars from limited resources, shows how even the smallest galaxies play by their own rules. Perhaps most remarkably, these unassuming dwarfs might hold the answer to one of cosmology's biggest puzzles, dark matter. Many appear to be embedded in massive halos of the invisible stuff, far outweighing their visible stars. Their motions and structures serve as natural dark matter detectors, helping astronomers map its distribution with precision no lab experiment could match. If dark matter behaves differently on small scales, as some theories predict, dwarf galaxies could be the first place we spot the discrepancy. From stellar fossils to dark matter laboratories, these tiny galaxies prove that size isn't everything. Their faint glow connects us to the universe's earliest days, their struggles and survivals mirroring the grand narrative of cosmic evolution. Every time astronomers discover a new ultra-faint dwarf or trace another stellar stream, they're piecing together a story written not just in the brilliance of giant galaxies, but in the quiet persistence of the smallest ones. And in that story, we find the humbling truth that even the mightiest structures owe their existence to the most unassuming beginnings. Right now, we're living in the universe's golden age of light, a brief window where stars blaze, galaxies collide, and cosmic recycling operates at full throttle. But this era won't last forever. As the universe expands and dark energy accelerates its pace, the very processes that built galaxies will gradually wind down. The gas clouds that once birthed countless stars are being depleted, either locked away in aging stellar remnants or flung into intergalactic voids by galactic winds. Future astronomers, if any exist, might gaze upon a night sky where new stars are rare jewels rather than common sights, their birth spaced across epochs rather than centuries. Yet even as star formation slows, the recycled light from earlier cosmic epochs continues its journey. Every photon emitted by the first stars, every burst of quasar radiation, every supernova's final flash still travels through the void, carrying immutable records of the universe's youth. Some of this ancient light gets absorbed and re-emitted by interstellar dust, its wavelength stretched but its story intact. Other photons traverse billions of light years unimpeded, their faint whispers detectable only by our most sensitive telescopes. This light forms a cosmic palimpsest, layer upon layer of history written across the sky, waiting to be decoded. The most distant galaxies we observe today already hint at this future. Their light, emitted when the universe was a fraction of its current age, reveals frenetic star formation rates compared to modern galaxies. over time that vigor fades. Spiral galaxies exhaust their gas reserves, their arms fading as star birth dwindles. Elliptical galaxies, already dominated by aging stars, grow redder and dimmer. Even the brilliant quasars that once illuminated the cosmos will eventually quiet, their supermassive black holes starved of fresh material to consume. The universe's recycling program doesn't halt, it simply operates on ever longer timescales, its rhythm slowing like a great clock winding down. Ironically, this gradual darkening makes our present era all the more extraordinary. We exist at a cosmic crossroads, late enough to observe the universe's history written in light, yet early enough to witness its ongoing creativity. The Milky Way still forms new stars at a rate of about 1 solar mass per year. Supernovae periodically flash in nearby galaxies, their explosions seeding space with fresh heavy elements. Even our own solar system bears witness to this active recycling: the oxygen we breathe, the iron in our blood, even the uranium in Earth's crust were forged in stars that died before our sun was born. But the universe's story doesn't end with fading light. In the far future, long after the last stars flicker out, the remnants of galaxies will continue their slow dance. Brown dwarfs, failed stars too small to ignite, might occasionally collide, sparking brief flares in the darkness. Black holes will devour the last traces of stray gas, their accretion disks glowing faintly before vanishing entirely. And all the while, the photons from long-dead stars will keep traveling, their wavelengths stretched so far by cosmic expansion that they fade into undetectability. The universe won't so much end as unwind, its energy diffusing into an ever-cooling expanse. For now, though, we're privileged witnesses to cosmic vitality. Every telescope image of a star-forming nebula, every spectrum revealing heavy elements in distant quasars, every simulation of colliding galaxies connects us to this grand recycling process. The universe has turned starlight into matter and matter back into light for billions of years, and we're here to trace its footsteps. That makes our era not just a chapter in cosmic history, but perhaps its most revealing one, when the universe could finally look back on itself and begin to understand its own origins. Simulating the early universe is like rewinding a cosmic film, but instead of guessing what happened, scientists now have supercomputers powerful enough to recreate those first moments with staggering precision. These digital universes don't just mimic the past, they let researchers test theories by tweaking variables like dark matter's behavior or the intensity of early starlight, watching how each change ripples through virtual galaxies. One groundbreaking simulation, Illusive, traced 13 billion years of cosmic evolution in months, starting from a near-uniform soup of particles and ending with intricate spirals and ellipticals eerily similar to those in our night sky. The key, gravity's patient pull, amplifying tiny density fluctuations imprinted during the Big Bang into the galaxies we recognize today. These simulations aren't just pretty animations, they're solving real mysteries. Take the missing satellites problem. Why do we see fewer dwarf galaxies orbiting the Milky Way than theories predict? By modeling dark matter's interactions, researchers discovered that early ultraviolet light might have sterilized gas in the smallest halos, preventing stars from forming and leaving them invisible. Other simulations revealed how supermassive black holes regulate star birth, their outbursts heating gas so efficiently that entire galaxies flicker between frenzied starbursts and quiet aging. Without these virtual experiments, such feedback loops would remain hidden, their effects too slow or subtle to observe directly. The most astonishing predictions come from collisions both real and simulated. When two protogalaxies merge in these digital realms, their gas doesn't just mingle. It triggers fireworks of star formation, ejecting material in winds so powerful they enrich intergalactic space. Astronomers later spotted these very outflows in real galaxies like Messier 82, their spectra matching the simulation's predictions line for line. It's as if the universe left breadcrumbs and supercomputers helped us follow them back to their source. Yet simulations also highlight gaps in our knowledge. Some early galaxies observed by the James Webb Space Telescope appear shockingly mature, their stars already old when the universe was barely a toddler. No current model fully explains this, forcing scientists to reconsider how quickly gas could collapse or how dark matter clustered in the cosmos' first moments. These discrepancies aren't failures, they're guideposts, steering theorists toward new physics like exotic dark matter particles or unexpected stellar life cycles. What makes these digital universes so revolutionary is their ability to connect dots across time. Light from the actual epoch of re-ionization takes 13 billion years to reach us, but simulations compress that journey into weeks, letting researchers watch ionization bubbles grow and merge like froth in a cosmic latte. By comparing these models to quasar absorption lines or the cosmic microwave background's polarization, we're piecing together how the universe transitioned from opaque fog to crystalline clarity. The ultimate goal isn't just to replicate what we see, it's to predict what we haven't. Upcoming telescopes like the Nancy Grace Roman Space Telescope will hunt for ultrafaint galaxies and primordial gas clouds predicted by simulations but never observed. Other models suggest rare, dark galaxies might exist, their star formation stifled by turbulent magnetic fields. If found, they'd validate decades of theoretical work, and if not, they'll send scientists back to the digital drawing board. In the end, these supercomputer universes are more than tools, they're time machines. By blending physics with computational brute force, they let us witness the unseeable. The first stars flickering to life, the cosmic web's filaments knitting together, even the explosive deaths that seeded space with the elements for planets and life. Every line of code is a step closer to answering the grandest questions, not just how galaxies formed, but how we came to trace their light across the void. The hunt for population 3 stars is one of astronomy's greatest detective stories, a search for celestial ghosts that shaped the cosmos but vanished without a trace. These first-generation giants, born from pure hydrogen and helium, were the universe's original alchemists, forging the first heavy elements in their cores and flooding space with the ultraviolet light that ended the cosmic dark ages. Yet despite their monumental role, not a single one has ever been seen directly. Their brilliance was fleeting, their lives measured in mere millions of years, and their light stretched to infrared oblivion by 13 billion years of cosmic expansion. But astronomers aren't giving up. They're turning the universe itself into a magnifying glass, using every trick in the book to catch even a glimpse of these elusive pioneers. One promising strategy involves quasars' distant beacons whose light cuts through the early universe like a flashlight beam. As that light travels toward us, it passes through clouds of primordial gas, some of which might have been enriched by population 3 supernova. The resulting absorption lines in quasar spectra act like cosmic barcodes, revealing the chemical fingerprints of elements scattered by those first stellar explosions. In 2022, the James Webb Space Telescope spotted a quasar whose light showed an unusual ratio of magnesium to iron, a potential smoking gun for material processed by a population 3 star's violent death. It's not a direct observation, but it's the next best thing, forensic evidence of their existence written in the chemistry of the early cosmos. Gravitational lensing offers another path forward. When massive galaxy clusters bend spacetime, they act like natural telescopes, magnifying faint objects behind them. In 2018, Astronomers used this effect to detect a candidate galaxy so distant its light came from just 250 million years after the Big Bang. Within its glow, they found no traces of heavy elements, a tantalizing hint it might host population 3 stars. The challenge, distinguishing their light from the surrounding gas, is like trying to spot a single match flame in a forest fire. Future observations with Webb's infrared eyes might finally separate the signal from the noise, revealing these stars not as individuals but as collective blurs in the universe's oldest neighborhoods. There's even a chance we've already captured their dying moments without realizing it. Short gamma-ray bursts, fleeting flashes of high-energy light, could be the final cries of population 3 stars collapsing directly into black holes. Unlike modern supernova, these explosions might leave no heavy element signatures, vanishing as suddenly as they appeared. Telescopes like the upcoming Vera C. Rubin Observatory could scan the skies for these ephemeral events, piecing together their origins from the faint afterglows they leave behind. The irony is profound. Population 3 stars were likely the brightest objects of their era, yet they're now the hardest to see. Their light, once so fierce it re-ionized the cosmos, has been diluted by the expanding universe to near invisibility. But if we do find them, it would be like uncovering the first pages of a cosmic origin story, one where the universe's first sparks ignited the chain reaction that led to everything we know. Every galaxy, every planet, every atom in our bodies owes something to those vanished giants. The hunt isn't just about nostalgia for the past. It's about understanding how the raw, early universe learned to build the ingredients for complexity, and ultimately for us. The cosmic microwave background isn't just an echo of the Big Bang. It's a fossilized blueprint for everything that followed. Imagine peeling back the layers of the universe to reveal its infancy, a time when space was a seething plasma of particles and light, too hot and dense for atoms to form. Then, suddenly, the cosmos cooled just enough for electrons to latch onto protons, creating neutral hydrogen and unleashing a flash of radiation that still permeates every cubic inch of space today. That flash, now stretched by expansion into faint microwaves, is the CMB, a baby picture of the universe, frozen in time when it was just 380,000 years old. But this snapshot isn't uniform. If you look closely, you'll spot subtle variations, tiny fluctuations in temperature, some regions slightly hotter, others cooler. These imperfections are the universe's birthmarks, the quantum ripples from the Big Bang magnified by expansion into the seeds of cosmic structure. A difference of just 1 part in 100,000 might seem insignificant, but over billions of years, gravity amplified these faint wrinkles, pulling matter into the denser regions while leaving the voids behind. Those overdense patches became the nurseries for the first stars, the proto-galaxies, and eventually the sprawling cities of stars we call galaxies today. The CMB's patterns are like a cosmic fingerprint, encoding secrets about the universe's composition and fate. By mapping these fluctuations with satellites like Planck and WMAP, scientists have decoded astonishing details: how much of the universe is dark matter, how fast space is expanding, even the geometry of the cosmos itself. One striking feature is the so-called acoustic peaks, ripples in the CMB where sound waves in the early plasma left their mark. These peaks are cosmic echoes, revealing how matter and light once danced together in a tight gravitational embrace before finally parting ways. What's truly remarkable is how these ancient fluctuations connect to the galaxies we see now. The densest spots in the CMB align eerily with today's galaxy clusters, as if the universe left a trail of breadcrumbs from its infancy to the present. Simulations show that the same regions glowing slightly brighter in the microwave background are the ones where dark matter later pooled, drawing in gas and igniting stars. It's a staggering continuity. The universe's first light didn't just fade away. It sculpted the distribution of matter, setting the stage for everything from spiral galaxies to supermassive black holes. Yet the CMB isn't just a relic, it's still shaping the cosmos. Photons from the CMB interact with electrons in galaxy clusters, a phenomenon called the Sunyaev-Zeldovich effect that lets astronomers detect invisible structures. Meanwhile, the polarization of CMB light carries clues about cosmic inflation, the universe's explosive growth spurt in its first fraction of a second. Some theories even suggest that primordial magnetic fields, woven into the fabric of space during this epoch, might have left faint swirls in the CMB's polarization, a ghostly signature waiting to be uncovered. When we look at the CMB, we're not just seeing light, we're witnessing the universe's first act of recycling, the moment it transformed from a featureless plasma into a canvas of potential, where every flicker of temperature became a future galaxy. Those photons have traveled for 13.8 billion years to reach us, carrying a message from the dawn of time. The universe didn't build itself at random. It followed a blueprint written in the language of light, and we're only just beginning to read it. The void between galaxies might seem like an endless, empty expanse, but it's actually a bustling reservoir of matter and energy. The intergalactic medium, or IME, is a vast ocean of gas so thin it makes Earth's best vacuum chambers look crowded. Yet despite its ghostly density, this diffuse material holds most of the universe's ordinary matter, hydrogen and helium left over from the Big Bang, laced with traces of heavier elements forged in the hearts of long-dead stars. Every time a supernova explodes or a quasar blasts out jets of plasma, they inject fresh material into this cosmic reservoir, enriching it with the building blocks for future galaxies. What makes the IGM so fascinating isn't just what it contains, but how it behaves. This gas isn't static, it flows along invisible filaments of the cosmic web, funneling toward galaxy clusters like rivers feeding a sea. When galaxies collide, their gravitational tug can strip gas from their outskirts, sending it spiraling into the IGM. Conversely, when conditions are right, pockets of this gas can cool and collapse, raining back down onto galaxies in a process astronomers call cosmic recycling. Imagine a water cycle, but on a scale so vast it spans billions of light-years. Evaporation, condensation, and precipitation played out with galaxies instead of clouds. The IGM also acts as a cosmic filter for light. When photons from distant quasars travel through it, certain wavelengths get absorbed by the gas, creating dark lines in the spectrum known as the Lyman alpha forest. Each line corresponds to a different cloud of hydrogen along the line of sight, mapping the IGM's structure in exquisite detail. It's like shining a flashlight through fog and seeing shadows of every droplet except here. The droplets are gas clouds larger than galaxy clusters, and the flashlight has been traveling since the universe was a fraction of its current age. But the IGM isn't just a passive backdrop, it's an active player in galactic evolution. In the early universe, ultraviolet light from the first stars and quasars ionized this gas, tearing electrons from hydrogen atoms in an event called re-ionization. That process didn't just make the universe transparent, it heated the IGM to temperatures of tens of thousands of degrees, altering how and where future galaxies could form. Even today, the IGM's temperature and density influence how galaxies grow, acting as a thermostat that regulates star formation across cosmic time. Some of the most surprising discoveries about the IGM come from what's missing. Observations show far less cool gas than expected, suggesting something. Perhaps supermassive black holes or galactic winds is constantly reheating it, preventing it from collapsing into new stars. Other studies reveal vast bubbles of million-degree gas, likely inflated by ancient quasar outbursts that pushed the IGM aside like a cosmic plow. These structures aren't just fossils, they're dynamic remnants of the universe's most violent events, still shaping the flow of matter billions of years later. The intergalactic medium might be invisible to the naked eye, but its fingerprints are everywhere. The oxygen in our atmosphere, the iron in our blood, even the calcium in our bones, all were once part of this vast reservoir, cycled through generations of stars before finding their way into our solar system. It's a humbling thought. The space between galaxies isn't empty at all. It's the universe's ultimate recycling center, where nothing is ever truly lost, only transformed, waiting to begin the cycle anew. Gravity doesn't just pull, it bends, warps, and magnifies, turning the cosmos into a vast funhouse of mirrors. When light from a distant galaxy travels past a massive object like a galaxy cluster, space-time itself curves around that cluster, distorting the light's path like a prism twisting a beam of sunlight. The result, a natural telescope forged by gravity that can amplify the faint glow of galaxies so distant they'd otherwise be lost in the void. This is gravitational lensing, one of Einstein's most dramatic predictions, and it's revolutionizing how we see the early universe. Take the galaxy cluster Max J0647 plus 7015, for example. Its immense gravity acts like a cosmic magnifying glass, bending light from galaxies behind it into vivid arcs and smears. One of those distorted smudges turned out to be a galaxy from just 400 million years after the Big Bang, one of the youngest ever observed. Without lensing, its light would have been far too faint for even the James Webb Space Telescope to detect. But thanks to nature's telescope, astronomers could study its starlight in detail, uncovering clues about how the first galaxies recycled primordial gas into stars. The magic of lensing isn't just magnification, it's distortion. The way light bends reveals hidden details about the lens itself. By mapping the warped images of background galaxies, scientists can reconstruct the distribution of mass in the foreground cluster, including its invisible dark matter halo. It's like watching ripples on a pond to deduce the shape of a submerged rock. Some clusters, like Able 1689, contain so much dark matter they create multiple images of the same background galaxy, a phenomenon called an Einstein cross. These cosmic mirages aren't just curiosities, they're precision tools for weighing the universe's unseen scaffolding. Lensing also lets us peer deeper into cosmic recycling than ever before. When astronomers study lensed quasars, they're not just seeing the quasars themselves, they're observing how their light interacts with gas clouds along the line of sight. Each absorption line in the quasar's spectrum is a fingerprint, marking where heavy elements from ancient supernova were mixed into the intergalactic medium. The most surprising discovery, some of these clouds are far more enriched with carbon and oxygen than expected, suggesting early galaxies spewed out metals much faster than models predicted. But lensing isn't flawless. The same distortions that magnify also stretch and shear, turning spiral galaxies into surreal streaks. Reconstructing their true shapes requires sophisticated algorithms, a cosmic game of undo the distortion. Sometimes the universe gets creative. Clusters like the Bullet Cluster produce lensing patterns so complex they look like abstract art, with dark matter and gas separated by violent collisions. These messy lenses are gold mines for astrophysicists, proving dark matter exists and showing how it behaves differently from ordinary matter. The future of lensing is even more exciting. Projects like the Vera-C Rubin Observatory will scan the sky for thousands of new lenses, creating a census of cosmic magnification. Meanwhile, astronomers are hunting for rare, double lenses, where two clusters align perfectly to amplify light from the universe's first stars. These layered lenses could reveal population 3 stars directly ghosts of the cosmic dawn, finally dragged into view by gravity's relentless pull. From unveiling dark matter to spotlighting the universe's youngest galaxies, gravitational lensing is more than a neat trick of physics. It's a reminder that the cosmos isn't just something we observe, it's an active participant, shaping the light we see and hiding clues in plain sight. Every warped image, every stretched arc, is a puzzle piece in the story of how the universe recycled its first light into the galaxies we call home. And with each new lens we discover, the picture gets clearer. Neutrinos are the universe's most elusive architects, ghostly particles so light they barely register as matter, yet so numerous they outnumber atoms by billions to one. Born in the unimaginable heat of the Big Bang and later forged in the hearts of stars, these cosmic phantoms zip through space at nearly the speed of light, barely interacting with anything in their path. A single neutrino could pass through a light year of solid lead without a single collision. Yet despite their near invisibility, neutrinos may have played a hidden role in shaping the galaxies we see today. Their influence wasn't through brute force but through sheer numbers, a whisper so persistent it subtly steered the course of cosmic history. Picture the early universe, a seething cauldron of particles and energy. Neutrinos, born in the first second after the Big Bang, outnumbered protons and electrons by such a staggering margin that even their feeble interactions added up. As they streamed outward from the densest regions, they carried energy with them, smoothing out the primordial soup just enough to alter where matter eventually clumped together. Think of it like a crowd of dancers moving through a room. Even if each person barely brushes against others, their collective motion reshapes the entire space. These tiny nudges may have determined which pockets of gas grew into galaxies and which remained barren voids. The fingerprints of this neutrino ballet are still visible today if you know where to look. The cosmic microwave background, that ancient afterglow of the Big Bang, shows faint patterns that match what simulations predict if neutrinos subtly suppress the growth of small-scale structures. In other words, regions where neutrinos were most active tend to have fewer dwarf galaxies than expected, as if their presence gently smoothed the cosmic landscape. It's a subtle effect, like finding a faint watermark on a sheet of paper, but it's there a testament to how even the weakest forces can leave lasting imprints when applied across the entire universe. Neutrinos didn't just shape galaxies, they also carried secrets about the universe's hidden inventory. For decades, scientists assumed these particles were massless, until experiments revealed they have a tiny but measurable weight. That discovery was revolutionary because neutrinos' mass affects how they move through space, which in turn influences how cosmic structures form. Heavier neutrinos would have slowed down earlier, clustering more tightly and leaving a stronger mark on galaxy distribution. By mapping galaxies and comparing them to models with different neutrino masses, astronomers are effectively weighing the universe's most elusive particles using the cosmos itself as their scale. What's astonishing is that neutrinos continue shaping the universe even now. Every second, trillions of them pass through your body, remnants of ancient supernova and nuclear reactions in the sun. Some are relics from the Big Bang itself, older than atoms or light, still traveling after 13 billion years. When astronomers detect high-energy neutrinos from distant galaxies, they're not just observing astrophysical events, they're tracing a hidden network of cosmic interactions, one that began before the first stars ignited and will endure long after the last ones fade. The story of neutrinos is a reminder that the universe builds its grandest structures through both the obvious and the imperceptible. Gravity may have drawn the blueprint, dark matter may have laid the foundation, but neutrinos, silent, swift, and countless, were the subtle hands that helped sculpt the final form. Without them, the cosmic web might look profoundly different, its voids emptier, its clusters denser. So the next time you gaze at the night sky, remember, the galaxies above weren't just shaped by what we can see. They were also molded by the whispers of particles so faint, we're only just learning to listen. The universe speaks in more than just light. It whispers through gravitational ripples and hums in the language of ghostly particles. Modern astronomy has cracked open a new era where telescopes no longer work alone. They're part of an orchestra, detecting not just photons but gravitational waves and neutrinos, each messenger revealing a different layer of cosmic truth. Imagine trying to understand a thunderstorm by only seeing the lightning. You'd miss the rumble of the thunder, the shift in air pressure, the scent of rain. That's what studying the cosmos with just light was like. Now we're finally hearing the full symphony. Take neutron-star collisions, some of the universe's most violent and creative events. When two of these ultra-dense stellar corpses spiral into each other, they don't just flare up in a burst of light. They shake space-time itself, sending out gravitational waves that ripple across billions of light years. In 2017, detectors LIGO and Virgo caught these waves from a merger dubbed GW170817. Seconds later, telescopes from gamma ray to radio spotted the counterpart light show. Together, these signals revealed something astonishing. The fireball forged gold, platinum, and other heavy elements in real time, scattering them into space like cosmic confetti. Without multimessenger astronomy, we might never have proven where these metals, the very ones in your jewelry or smartphone, truly come from. But gravitational waves are just one piece of the puzzle. Neutrinos, those nearly massless particles that barely interact with matter, add another dimension. When a star explodes as a supernova, 99% of its energy escapes as neutrinos, while just 1% becomes visible light. In 1987, detectors on Earth caught neutrinos from supernova 1987 hours before its light reached us. These ghostly particles gave us a head start, offering a sneak peek into the star's violent death before the optical fireworks began. Today, instruments like IceCube in Antarctica track high-energy neutrinos back to their origins, like cosmic breadcrumbs leading to supermassive black holes or colliding galaxies. The real power of multimessenger astronomy lies in its contradictions. Sometimes what light conceals, gravitational waves reveal. For instance, black hole mergers are completely dark. No light escapes their event horizons. But their gravitational waves paint vivid portraits of the chaos, detailing the black hole's masses, spins, and even how they wobbled as they merged. Other times, neutrinos act as scouts, pinpointing cosmic particle accelerators that visible light alone can't explain. In 2018, a single high-energy neutrino led astronomers to a blazing galaxy 4 billion light-years away, where a supermassive black hole was flinging particles across the cosmos at nearly light speed. This approach is rewriting astrophysics textbooks. Gamma-ray bursts, once thought to come in two distinct flavors, now appear more complex thanks to combined gravitational and electromagnetic data. Dark matter searches have gained new avenues as scientists cross-reference neutrino detections with gravitational lensing maps. Even the expansion rate of the universe, a number fraught with discrepancies, might find resolution when measured through multiple cosmic messengers. Each time we add another observational thread, the tapestry of the cosmos grows richer and more intricate. The future of multimessenger astronomy is brighter than a quasar at full tilt. Upcoming observatories like the Einstein telescope will catch gravitational waves from the universe's first stars, while next-generation neutrino detectors could spot particles from the Big Bang itself. Space-based interferometers might one day track mergers back to the cosmic dawn, and AI is learning to correlate these signals in real time, turning raw data into instant discoveries. We're no longer just observers of the universe, we're active listeners, decoding its secrets through every means it speaks. And with each new messenger we harness, the cosmos becomes less like a silent movie and more like an IMAX experience, immersive, multidimensional, and utterly awe-inspiring. There's a humbling truth hidden in the story of recycled light, one that transforms how we see ourselves in the grand tapestry of the cosmos. Every atom of oxygen in your lungs, every speck of iron in your blood, was once part of a star that died billions of years ago. The calcium in your bones was forged in a supernova explosion, its shock waves scattering those elements across space until they found their way into the cloud that birthed our solar system. Even the light reaching your eyes from distant galaxies isn't just illumination, it's a cosmic messenger, carrying traces of its journey through ionized gas and gravitational fields, a thread connecting you to the universe's first dawn. This isn't just poetic metaphor, it's physical reality. The carbon in your DNA, the nitrogen in your cells, even the gold in a wedding ring, all were cooked in stellar furnaces and scattered by cataclysmic explosions long before Earth existed. When you gaze at the stars, you're not just an observer looking outward. You're the universe looking back at itself, a collection of atoms that once drifted between galaxies, now assembled into something capable of wonder. That shift in perspective changes everything. It turns astronomy from a distant science into a personal origin story, where the cosmos isn't out there, but woven into the fabric of your being. The implications ripple far beyond biology. Consider time itself. The light from the Andromeda Galaxy traveled 2.5 million years to reach us, meaning when you see it, you're peering into the past, back when early humans were just discovering fire. The Hubble Ultra Deep Field captures galaxies as they were over 13 billion years ago, their light only now arriving after crossing the vastness of space. In a very real sense, observing deep space is time travel, with every photon a fragment of history. This collapses the distance between past and present, making the ancient universe feel startlingly immediate. Yet there's a paradox here. For all that starlight connects us to cosmic history, much of the universe is already slipping beyond our view. Dark energy's accelerating expansion ensures that distant galaxies will one day fade from sight entirely, their light stretched beyond detectability. We live in a privileged sliver of time, a brief window where the universe's history is still legible. Future civilizations might arise in a cosmos where the Big Bang's afterglow has redshifted to nothing, leaving them with no clues to their origins. Our ability to trace the lineage of atoms and light isn't just scientific progress, it's a fleeting opportunity, a cosmic inheritance we're uniquely positioned to receive. Perhaps the deepest revelation is how thoroughly this reshapes our sense of scale. The human lifespan feels insignificant against billions of years, until you realize your body contains atoms that witnessed the universe's youth. A single human seems tiny compared to a galaxy until you recognize that a galaxy's purpose, in some sense, was to forge the materials for life. The boundaries between us and the cosmos dissolve, revealing a continuity of matter and energy that spans from the first stars to the thoughts in your brain. You aren't just in the universe, you are the universe, a localized expression of its capacity for self-awareness. This perspective doesn't diminish human significance, it expands it. The universe didn't passively arrange itself into complexity. It fought for it, through supernova that seeded space with heavy elements, through galactic collisions that mixed those ingredients, through billions of years of trial and error to reach a state where atoms could ponder their own existence. Your ability to reflect on starlight is the cosmos's way of understanding its own journey. In the end, the story of recycled light isn't just about photons and galaxies. It's about how the universe, step by step, learned to turn chaos into consciousness, and why that matters for whatever comes next. From the first flickers of light after the Big Bang to the dazzling galaxies we see today, the universe has been engaged in an endless cycle of recycling, a cosmic dance where nothing is ever truly lost, only transformed. Every photon emitted by the earliest stars, every atom forged in supernova explosions, every ripple of gravity from colliding black holes has played a part in weaving the tapestry of the cosmos. This grand story isn't just about distant celestial phenomena. It's the story of how raw hydrogen and helium evolved into the complexity that makes our existence possible. The iron in our blood, the oxygen we breathe, even the light from our sun, all were once stardust scattered across the void, gathered and remixed over billions of years. What's astonishing isn't just the scale of this recycling, but its elegance. The universe operates like a vast, self-regulating machine, where the death of one star seeds the birth of another, where galactic winds carry heavy elements into the intergalactic medium, only for gravity to pull them back into new generations of planets and stars. Even the darkest corners of space play their part. Black holes, often seen as destructive monsters, act as cosmic regulators, their outbursts heating gas and preventing galaxies from burning out too quickly. Dark matter, invisible and enigmatic, provides the scaffolding for this entire process, its gravitational pull guiding ordinary matter into the structures we recognize today. Yet this story is far from finished. Right now, stars are dying in spectacular supernova, scattering fresh elements into space. Galactic collisions are triggering bursts of new star formation, their light adding to the cosmic background. Even our own Milky Way is on a collision course with Andromeda, a future merger that will reshape both galaxies in ways we can barely imagine. The universe doesn't rest, it reinvents itself continuously, turning destruction into creation on scales that defy comprehension. The beauty of this narrative is that we're not just observers, we're participants. Every time we look up at the night sky, we're engaging with a history written in light, one that connects us directly to the universe's earliest moments. The photons hitting your retina might have traveled for millions of years, carrying echoes of distant quasars or the last glow of a dying star. In a very real sense, stargazing is time travel, a way to touch the past while standing firmly in the present. As technology advances, our understanding of this cosmic recycling deepens. Telescopes like James Webb peel back layers of time, revealing galaxies in their infancy. Gravitational wave detectors listen for the ripples of black hole mergers, events that redistribute matter and energy across the cosmos. Each discovery adds another verse to the universe's epic poem, showing us how chaos gives way to order and how simplicity blossoms into complexity. So the next time you step outside on a clear night, take a moment to let the scale of it all sink in. Those pinpricks of light aren't just distant suns, they're the end result of a process that began in darkness, a chain reaction of creation and renewal that has been unfolding for 13.8 billion years. You're not just looking at the stars, you're seeing the universe's greatest masterpiece, a work in progress, forever evolving, forever recycling, forever revealing new wonders to those